Okay, hello again. This is the course of data structure and algorithms, and today we are going to discuss about the concept of tree. Okay, tree. I think in Korean is namu. So what is tree? And we are going to discuss the details about this tree. And for this chapter, we are going to discuss about the concept of tree, the basic tree ADD, and then there are some concept about traversal. So what is traversal? So it's kind of traveling in the tree. And the other kind of tree, we will learn about the binary tree and link structure tree and array-based tree. So first, let's deal with the tree ADD. What is tree actually? So yeah, we call this is a kind of tree. So when you have one of the node, and then you will have another node in below part, and then you have another node in below part. So we call it as tree. Okay. So tree in computer science, it is an abstract model of hierarchical structure. So there is a hierarchy. For example, this is a company. Okay, so this is the computers are us. Yeah, just want to make the name. And then in this company, we have the sales department, manufacturing department, and R&D department. For the sales, we have the US and the other international. For example, Europe, Asia, Canada. And for example, for the manufacturing, we have the other production line, for example, for laptops and for desktops. Okay, so those kind of hierarchy, we can put it into a tree, or we can put it into the hierarchical structure. So the tree consists of nodes, and the nodes we can say it is a parent and child relation. So some application of the tree are the organization charts like this one, or we can also think about the file system. So if you are using your computer, so you can see the file system using the tree and some programming environments. So yeah, in the programming environment, if you have your class and if you have your data and etc., so that's also using a tree. Some terminology that you need to know about the tree is this one. So first you need to know that the tree contains root. Okay. So what is root? So root is this one, the node without parent. So there is no upper node. Okay. And we have also another term which is internal node. What is internal node? Okay. So the internal node is node with at least one child. We have child. Okay, A is internal node because A has B. So at least we have one child. What about B? B also a child, an internal node because B has child E and F. What about F? F is also internal node because F has I, J, and K. What about E? No, E is not internal node because E has no child. What about C? Yeah, C is also internal node because it has G and H. What about D? D is not. Okay, then yeah, we can say that the internal node is A, B, and C, and then F. So those are the internal nodes. What about the external node? The external node, or we call it also leaf. Okay, so the external node is node without children. So node without children, you can see this is E, and then we have I, J, K, and then we have G, and then we have H, and we have D. Okay. We also have another terminology we call ancestors. Yeah, ancestors. So ancestors means the the parent or the grandfather or the grandparent, the grandparents. Okay. So we call this is parent, grandparent, grandparent. Okay. So if it is parent, so like what is the parent of F? So the parent of F is B. What is the grandparent of F? Okay. The grandparent of F is A. Okay. If I want to know what is the grandparent of K, so the parent of K is F, the grandparent of K is B, and the grandparent of F is A. Okay. What about depth? Okay. So the depth of a node, so it means the number of ancestors. The number of ancestors. So if I want to check what is the depth of I, So I can say this is 3 because I have 1, 2, and 3. What about the depth of edge? The depth of edge is 1 and 2. Okay, so that's the depth. What about height? Okay, so the height means the maximum depth of any node. Okay, so it's the concept is the same, okay, but we can just say that this is the tree. So the whole tree we have the height goes to 3. If we have the ancestor, we also have descendant. Okay, what is descendant? So the same idea. If we have the ancestor, it means we go to the upper side. But if descendant, we go to the downside. So the downside is we call it child or grandchild or grand-grandchild. We can also have another terminology. We call it subtree. Okay, what is subtree? The subtree is the tree inside a tree. Okay, so a tree consisting of a node and its descendant. So we call this is the C, D, C, G, and H. So this also it's a subtree because it is a tree. Yeah, a tree should have those things like the root and the internal node. Yeah, it should have the external node. It should have the ancestor, head, descendant. Okay, so here is also a tree because at least it has a root, it has the internal node which is C, it has the external node G and H. Okay, so we call this is also a tree. So the tree ADD it contains of the generic method like the length, how many nodes are in the tree, is empty, whether the tree is empty or not, and I would like to know the position, and we can do the iteration. Okay, the assessor methods are the root. So I want to know what is the root of the tree. Parent, what is the parent of a particular node. Children, so if I have many children, so it will be a iterator. Okay. And then the number of children of a particular node. So I want to know if a node has 3 children, then it will return the number of children. The query method, it contains of 2, which is isLeaf and isRoot. So whether the node is a leaf or not. If it is a leaf, then it returns true. If it is not leaf, then it returns false. Root, it is also the same, true or false, because it is Boolean. The update method means I want to replace a particular node with another object. Okay, so P means the position and then O is the object. So additional update methods may be defined by data structure implementing the tree ADD. So this is the basic tree ADD. And if you have your own implementation, you can try by your own to build your own query methods or other accessor methods. For example, I want to access the internal node. Then yeah, you can do with your own method for this one. So the abstract tree class in Python, yeah, as I mentioned to you, it used the basic idea of the other data structure like the generic methods, yeah, but it's also containing the position. So if you already remember the positional list, it contains the position. If the position has the element, and then we want to know whether the element is equal or not equal. And then I want to know whether the tree is a root, or what is the parent of P, what is the number of children of P, and then what is the children of P, what is the length, and is root, is leaf, and is empty. Okay, so those are the abstract tree class in Python, and you can build your own method for the future implementation. Now, when you have a tree, you need to consider how can you access the node. Okay? Because accessing the node will determine the operation. So for example, I have one method, we call it the pre-order. Okay? So the pre-order traversal means I want to, sorry, before I explain the pre-order, I would like to mention what is traversal. Okay? So a traversal visits the node of a tree in a systematic manner. So I want to visit node another node, and another node, and another node. So it means you want to do like searching. Okay, so when you want to search, then you need to know what is the sequence of the searching in the tree. So we have one of the method, we call it the pre-order traversal. The pre-order traversal means a node is visited before its descendant. Okay, so let's see. If I want to print a structured document, okay, so that can be also one of the implementation. So if first I go from the root, and then it goes to the descendant, yeah, so a node is visited before its descendant, so it goes to descendant, and then it goes to another descendant, okay, and then after I finish this descendant, I will go back to the parent, okay. Oops, okay, there is no other descendant here, then I will go to the next descendant, and after this I will go to the next node, which is 5. I will go to the next, which is 6. I will go to the next, which is 7. I will go to the next, which is 8, and then there is no other descendant. I will return back, and then I will go to the next node, which is 9. So we have the algorithm like this one, pre-order V. Okay. V is the node that we want to visit. So visit V. So this is visit 1. And for each child W of V, so for each child, so this is the child, this is the child, and this is the child, and then we will do again the pre-order. So this is a loop. Okay, you already know the recursion. So we're using the concept of recursion. Now we want to check pre-order W. So what is the pre-order W? Here we will check the pre-order W, and then we want to visit W. Okay, let's say this one. And then for each child W, or yeah, we can say this is the new one. This is the V is now the W. So we have a new W, which is this 3 and 4. Okay. So when we do the pre-order, we will visit this one, and then let's check. Is there any child? No, there is no child. So if there is no child, then you know the recursion will return back to the previous one. So after we return back to here, then we will go to the other child. This is this one. Okay, so that's the pre-order traversal will do. The other way to visit the nodes, we can say as the post-order traversal. The post-order traversal means a node is visited after its descendant. So when we are doing the traversal, we want to do from the leaf node. Okay, so this is the first one. Okay, so for example, the application about the computing the space used in your computer. Okay, so if you want to know how much you spend for the space, so using the post order, you will check the for every node is from the child, and you know, if for each child of W, for each child W of V, so we have the child, we have here, we have the child, here we have the child. Okay, so we will do the post order first, and then after we know this child, we will check another child. Okay, and then after we have this, and we will go to the next, which is the ancestor. So after we have this ancestor, we go to another child, and then we go to another child, and then we go to another child, and then we go to the ancestor. Again, we go to another child, and there is no other child here, then we go to the parent. Okay, so this kind of things can be the post order traversal. So you start from the bottom part. If the pre-order, it's start from the upper part. The other kind of trees might be interesting for you, which is about the binary trees. So binary tree is a tree with the following properties. So each internal node has at most 2 children. So we have here, this is the node, at most 2 children. So there will be no more than 2. Okay, and it's exactly 2 for proper binary trees. Okay, we have the word proper. Proper means, yeah, we have exactly 2, but if you are just binary tree, then it maybe have only 1. Okay, for example, this one, yeah, you have 2. Okay, for this one is proper binary tree because it contains 2 children for every node. So the children of a node are an order pair. What is order pair? So if you have A, so this is to be from B and C. If we have P, then we have two children, and the node will be D and E. So it's always order, and the order will be from the left and right. Okay. And the alternative way for this one, I guess if you still remember the recursive, okay, the recursion. So the recursion can use also this kind of binary tree. If you still remember when we have the binary sum, okay, we want to sum from the left and then we want to sum from the right. So this kind of binary tree, it can be a tree consisting of single node. Okay, so it is the basis, and then a tree whose root has an ordered pair of children, it's of which is a binary tree. So the recursive, it can be done with this kind of tree. If you still remember some application like the arithmetic expression, okay, the arithmetic expression can be also represented by binary tree. You will know about the sum. So the binary sum, you already know about that one. And then the decision process, it can be also regarded as the binary trees. And searching. So searching is also one of the application later. I think you already learned about the binary search. Okay. So if you have a list again, and if you want to search a particular value, you can just divide into two. You can see the low, mid, and high. If you know that the particular value is higher than mid, then you will just cut into half. Okay. Then etc. So those kind of application you can use with the binaries. So let's see if we have the arithmetic expression tree. So the arithmetic expression tree will be something like this one. So the binary tree associated with arithmetic expression, the internal node can be the operator, and the external node can be the operands. Okay? So for example, I have this arithmetic expression. So 2 multiplied by a minus 1 plus 3 multiplied by b. So the internal node will be the operator, which is the plus, multiply, minus, and multiplication. So we have this one, 2 multiply a minus 1. Okay, a minus 1 will be in the parenthesis. So after we have 2 multiply a minus 1, we will add the values with 3 multiply by b. Okay, so using this expression tree, it would be easier for you to calculate an arithmetic expression. Or in other kind of application, you can use with the decision tree. So decision tree is one of the result from the classification, or if you are doing the data mining stuff, you will need this kind of decision tree, or in your daily life, you will need also this kind of decision tree. For example, the internal node is a kind of questions. Let's say if you have the question is only yes or no, and the external node would be the decision. So want a fast meal? Yes. Then how about coffee? Yes. Then let's go. Sorry, I called brand here. Okay. How about coffee? Yes. Okay. Then let's go Starbucks. Or how about coffee? No. Then let's go Spikes. So Spike is a kind of restaurant. Is like, almost the same with like McGee, okay, something like that. And if you want to have a fast meal, no, then okay, on expense account you need to know the amount of the expenses. Then yes, okay, then Alforno is very luxury restaurant. Or if you want to on expense account, yeah, then you can figure out about the other like Cafe Paragon. Maybe this is less expenses. So those kind of decision is also important if you know the the possibility or the condition here. So when you have the proper binary tree, okay, this is the proper binary tree. What is proper binary tree? Yeah, you can see this one before. The proper binary tree is the internal node has at most 2 children, or exactly 2. Okay, sorry, exactly 2 is for the proper binary trees. So in this case, this is the exactly 2 of the children. Well, let's see. If I have n is the number of nodes, and e is the external nodes, and I is the internal nodes, and h is the head. So the properties will be like this one. E will be equals to I plus 1. What does it mean? E. E is the number of external nodes. So let's see this. Okay, let's see this binary tree. So what is E? E is the external node is 1, 2, 3, 4. Okay, so the E equals to 4. Okay, and then what is I? I is the number of internal nodes. So I will be 1, 2, 3. Okay, so it perfect with these properties. It fits with the properties. So the I plus 1 will be the E. Okay, then what about this one? N equals to 2E minus 1. And what is the number of nodes? Okay, 1, 2, 3, 4, 5, 6, 7. Okay, so n equals to 7. And then what is the 2e? E equals to external node, we are 4. Okay, e equals to 4. Okay, so there's if you want to calculate, then 2 multiplied by 4, 2 multiplied by 4 is 8. And after we have 8, we want to minus 1, then the result is 7. Okay, what about this one? H is less than equals to I. Okay, because the structure of the proper binaries can be this one and can be this one. So the H is the head. So we have 1, 2, 3, 4. Okay, so H is 4. And what is the number of internal nodes? Sorry, 1. Okay, yeah, 4 is. Oh, no. I think the head is 3, right? I is the number of internal nodes. Oh, okay, 1, 2, 3. So this is the head. The head is the number of ancestor. So 1, 2, 3. Okay, sorry, this is not 4. Okay, I made a mistake. So this one should be 3. Okay, okay, because the h is the number, the maximum that we have for the ancestor or the descendants from the top. So it means like 1, 2, 3. Okay, or this is 1, 2, 3. So h equal to 3, and the number of internal nodes is 3. Then we can have, yeah, it's 3. Then h is less than or equal to 3. What about this one? Properties. This is the h is less than or equal n minus 1 divided by 2. Then we have n, which is number of nodes. We have 7. 7 minus 1, it is 6. 6 divided by 2 is 3. Okay. What about this? E less than equal to 2 power of h. So h is the head. So 2 power of 3. Okay. And e, what is e? Is the number of internal nodes. So there are 4. So 4 will be less than or equal than 2 power of 3. Yeah, that's certain. And h is log base 2 of e. Log base 2 of e. E is the external node. So we have 1, 2, 3, 4. Okay. Log base 4. Log base 2 of 4. Then we can get this log 2 of 4. Okay. If you return back to the previous chapter, we learn about the concept of algorithms. So log 2 plus 4 is 2. Okay. So the h is greater than equal to 2. Okay. And the other properties is this one. So h is greater than equals to log 2 n plus 1 minus 1. So n minus 1. So what is n? N is 7. N plus 1 is 8. Okay. After we do the log, okay, log 2, 8, then it means 3. Okay. So 3 minus 1, then we have 2, and then h should be greater or equal to 3 minus 1. So those kind of the properties will be the properties to check the proper binary trees. Okay. So you can check also the same with this one. How can you check this one? Okay. So try with this property. So maybe this is one of the question in your exam. Maybe, I don't know. So the binary tree ADD is one of the ADD that you can use. For example, I want to know the tree, about the position the generic method of the tree, and then you want to know the root, you want to know the leaf, okay, and etc. So in the binary tree, you can also have the additional methods, which are, I want to know the left, I want to know the right, and I want to know the siblings. Okay, so yeah, those kind of things. The left is, yeah, I want to know if I have names, and then I want to know the left, I want to know the right, I want to know the sibling. So if the sibling is this one, then I want to know this one. If I know this one, then I want to know this one. Okay. So the update methods may be defined by the data structure implementing the binary tree ADD. So you can also define your own methods for making the binary tree. In the binary tree is also considered a traversal because we have only 2 children, then there will be also some ways to travel from the tree. So we call the in-order traversal. Okay? In-order traversal, it is a way to visit the node after its left subtree and before its right subtree. Okay? So using the in-order, so you can check the left and right. So first we will go to this one, and then go to the next, and then go to the left, and then go to the parent, and then go to the right, and then go to the upper side, and then go to this and this and this. So the algorithm is something like this one, in order v. Okay, what is in order v? We have the in order traversal. We want to visit the v. So v has a left child. If v has a left child, yes, it is true. Then in order left v. Oh, sorry, maybe it should be starting from here. It has left, yes, then it goes here. In order left v. And then we will check if there is a left, yes, left, then yeah, we'll go here. Now, is there any left child? No, there is no left child. Since there is no left child, then we will go here, visit v. So we will visit 1. Okay. After we visit 1, then it goes to check if v has a right child. So is there any right child? No. Then because there is no right child, then it will be written back. So this is another recursion. So because it is recursion, then we will go here, and then we will check, is there is there any left child? Because we already finished this one, then we will go to visit 2. After we visit 2, then it will check if v has a right child. It has a right child, yes, and then we will do in order right. So when we do the in order v, again we will check if v has a left child. Yes, it has a left child, so 3. So after we visit 1, and then 2, and then 3. Okay, and then after we visit 3, is there any left child? No. And then we will visit 3, and is there any right child? No, there is no child in the tree. Then we will return back because of the recursion, and so on. Okay. We can also do with this binary tree for the arithmetic expression. So in the arithmetic expression, if we have only left and child, yeah, we can use this expression. And yeah, especially if you are doing with this expression, we can use the print expression with the parenthesis. Okay, with the parenthesis, you can print the parenthesis before the traversing and after the traversing. Okay. The before the traversing, it means from the left subtree, and then the after traversing, it means the right subtree. So if we are in the left child, then you can put, for example, the opening parenthesis. And after you do the in order, you want to print the element. Okay, you want to print the element, and then if you check is there any right child, then after you do with this recursion, you will put the closing parenthesis. Okay, so this is the tree that you already learned before. Okay, so that's the way that's one of the application. And we can also do this one with the post order traversal. Okay, so the post order traversal here is a kind of way to check. The post order traversal is the way to evaluate the arithmetic expression because we have only 2, so it has left and right. So we can also make our own method by evaluating the expression v, and if it is a leaf, then return the element. If it is not a leaf, then let's check the operator in the left, and then let's check sorry, let's check the number on the left, and then let's check the number on the right, and let's do the operator. Okay, so it means if it is leafy, let's get this element, and then if not a leaf, then we will check what is this operator. So we will check the 2, and then we do to check operators. Because it's not finished, then we will check again, it is leaf, no, then we will go here, it is leaf, no, so we will go to this left, and then we will go to this right, and then we will store the operators. Yeah, so this is the, for example, 5, and then this is the 1, and then this is the minus. So we will return 5 minus 1 for this one. Okay, so those will be repeated, or the recursion, after all the trees are traversed. There's also another kind of traversal, we call it Euler tour. So this Euler tour is a generic traversal of binary tree, and it includes a special case of pre-order, post-order, and in-order. Okay, so it should walk around the tree and visit each node 3 times. So on the left it is pre-order, on below it is in order, and on the right it is post-order. So just go here, and then we want to check left, and then after we check this one, we will go to the below, to the upper side, and after we go to this, and then we will go to the right one. Okay, and then we left again, and then go to below, and then right, and so on. Okay, so this is the Euler tour. Okay, we will check one by one, but of course it will check all those nodes. Okay, and the Euler tour means I will go to every node, but the street will be only one, or the path. Okay, the path that I use this one is only one. Okay, I will not repeat this path, and I can repeat the node, but I will just use only one path in order to visit all the nodes. There is another concept about the trees, which using the link. Okay, so the link structure means I have the element, I have the parent node, and I have the sequence of the children node. Let's say I have P. P is the parent. Okay, so P, now P is the element, and there is no parent, and this is the next element. Okay, so you know the link. Okay, you know the link list. Okay, so in the link list we have the single and we have the double. So let's just consider this is only the link. Okay, I want to know what is the link. Then next I will have the link which is related with the element A, element D, and F. So B, I have the link to the element A, element D, and element F. For the element A, I have the parent, which is P. Okay, so this is the element. Okay, and then this is the parent node, and then this is the sequence of children node. So here is the element, this is the parent. Okay, the parent of A is P. What is the children? No children. Okay, so A, no children. What about D? For D, it has parent. What is the parent? It is P. What is the children? It has 2 children. So this is the sequence. So left and right. Okay, so the left and right. Okay, this is 3. Okay, not proper binary trees. So we have 2 children, which is C and E. So the C, okay, here. And what is the parent of C? The parent of C is D. What is the parent of E? The parent of E is D. Okay. What is the children? Empty. What is the children of E? Empty. Okay. So each of this link structure can be represented with at least 3 of data, which is the element data, the parent data, and the children data. In the link structure for binary trees, because you already know that the binary trees consists of left and right. Okay, so we can have the element, we can have the parent node, we have left child node, and we have right child node. Okay, we have the element. Okay, the element is in here, and then this is the parent, and then this is the left node, and this is the right node. So we can represent the tree like this one. This is the binary trees. Okay. If B has A, then this is the A, it is in the left, and D is in the right. Okay, And then we have the A. There is no children. What about D? D has a children. On the left is C, and on the right is E. But there is no children of C. There is no children of E. And the parent of C is D, and the parent of E is D. Okay. So this can be implemented using the positional ADD. The last one will be the array-based representation. So in the array-based representation, you have the tree, the proper binary trees. Yeah, you can use proper binaries, or you can have only the binary trees. But the representation will be in the array. Now, how can we change the trees into array? Okay, so you need to check this one. So the node v, okay, so the node v is stored at the A rank v. What is A rank v? Okay, let's see. I have the A. It is the rank of the root is 1. Okay, so 1. So you know the index in the array. The index in the array will start from 0. Okay, so because we have the index starting from 0, and I know that the rank start from 1. So what happened to the index 0 in array? Empty. Okay, so the index 0 in the binary trees will be empty, and the rank of the root, which is A, is 1. So the position, this is the array in index 1. The index 1 will have the value of A. Okay, now what happened about B? Okay, so okay, maybe I can just draw with the other representation like this one. Okay, so index 0, index 1, index 2, index 3, index 4, index 5, index 6, 7, 8, 9, 10, 11. Okay, 12. Okay, just I will finish this one. Maybe I can just erase the, oops, if I erase this one, maybe, okay, anyway, I will put this one like this. So now I will like to have the, because the index 0 is nothing, okay, then now I will change this. So the index 0 is empty, so the A, it will be from the A will be, the root is A, and it will be in the first one, so in index 1. What about B? B is in the rank 2. What is in the rank 2? So if node is the left child of parent node, then the rank of the node will be 2 multiply rank of the parent node. So because I know this is left, okay, so because it is left, then it will be 2 multiplied by, what is the rank of the parent node? The rank of the A is 1. Okay, so it means the result will be 2. Okay, what if this the right child? So the right child of the parent node will be 2 multiplied by rank parent node plus 1. So here is the rank, which is this right node. So 2 multiplied by 1, and then it will be plus by 1. So it will be plus by 1. It means it is 3. Then I know that B will be located in the index 2, and then D will be located in index 3. Okay, what about E? So E, I know that this is 2, okay, and then I want to know it is left. Left, it means 2 multiplied by rank parent node. So it is 2 multiplied by 2. Then the index will be 4. So the index 4, this is 0, 1, 2, 3, 4. Then it is E. Okay, and after I know this is E, then yeah, you can check the right node. It is 2 multiplied by 2, and then you will do this one first, plus 1. So the index will be 5. And we know if it is F here, and then I can check the C and J. So the same, 3 so we have it is in the left, and then 2 multiplied by 3, so it is 6 for C. Okay, and then for J it is 2 multiply by 3, and then we have plus 1. Okay, then we have the result as 7. So this J. Now we have next one is should be E, but there is no children of E. What about F? Okay, we have two children. F is G and H. So the left one is 2 multiplied by 5. What is 2 multiplied by 5? It is 10. What is the right one? Is 2 multiplied by 5 plus 1. Okay. So when we have this one, then the result will be 11. So the result of 11 will be, yeah, J is 7. So 8, 9 will be empty. 10 will be filled with G and H. Okay, and then, yeah, there is the result of this array. So the element of 0 is empty, and the element of 8 and 9 also empty. Of course, this empty is not a matter because you don't have the element. It's only that one. Okay, the element is empty or the element is known because there is no children here. Okay, so if you use this array-based representation, maybe it will consume some more spaces, but it doesn't matter. It still have the idea how to make it in a better representation of data structure. Okay. Yeah, I guess that's all. And if you want to take a look on the Jupyter notebook, so I already give you the code, but this is only the ADT. Okay, so there is no implementation. You can try with your ways for the implementation, and I think I will not explain this one because it depends on your necessity. If you need those for your project, okay, you can also use this one. And I hope that it will also explain how can you use in a particular application. For example, if you are using the binary tree for searching and etc., yeah, you can use this kind of tree. Okay, so I think that's all for this concept of tree, and hope you have a good study in your from the chapter 1 until the current chapter, and good luck for your exam. Thank you very much.